Formal hypothesis test. If conducting a formal hypothesis test to determine whether there's a significant linear correlation between two variables, use the following null and alternative hypotheses that use rho. Remember, that's rho. To represent the linear correlation coefficient. Okay, so null hypothesis. Null hypothesis is going to assume some parameter equals 0. So a lot of the times that's the mean. You'll assume the mean equals 0, and then we'll try to do something off of that. But in this case, we're talking about the population correlation coefficient. Okay. In other words, we're assuming that there's no correlation. We're assuming here, the null hypothesis is we're assuming that there is no correlation. The alternative hypothesis is just the opposite. So you don't have to assume, you don't have to make two assumptions. The null hypothesis, we're going to assume in this case that correlation coefficient of the population equals 0. Hopefully you'll see how that works here in a second. Now, a test statistic gives you this formula here, and it's a little bit silly to think of this formula because we've got so many other ways to use technology and get this same number. So this is kind of how you would do some stuff before we had technology using tables and stuff. I'll show you how to use that, but pretty much we're just going to use technology. Now, in -2 degrees of freedom, we've got an example that we've seen before where there were 23 data points. And so 23 minus 2 would be 21 degrees of freedom in the example that we've seen in this section. Number 6, hypothesis test using the p-value from the t-test. Use the paired chocolate/Nobel data to conduct a formal hypothesis test of the claim that there is a linear correlation between the two variables. Use 0.05 significance level with the p-value method of testing the hypothesis. Okay, so hypothesis test. We're going to start with that null hypothesis. You want to write kind of small here. Okay, so, notice we're talking about the claim that there is a linear correlation between the two variables. The null hypothesis, we're going to assume there's not. Assume that that equals 0, which is saying no correlation. So, the claim is we think there's some sort of correlation. The null hypothesis is assuming there isn't. We're assuming that that parameter, that correlation coefficient of the population equals 0. That's what we're doing for the null hypothesis. All right, so keep that in mind. If we didn't have technology, we would want to use this t number. All right, so let's start by finding that t number. The R for this example, you have to go back and look at it, I guess. Earlier in the notes, we found the R value, the sample correlation coefficient for this problem was 0.801. So inside that square root, we're going to have 1 minus 0.801 squared over, in -2 is talking about that degrees of freedom. Bless you. 23 minus 2 is 21. So once we do that calculation, I'm not going to type it in. Trust me on this. We get about 6.131. That is our t number there from that equation. So this textbook tells us to use table A3 to look at this number, and it's kind of hard to understand what to do, but remember this number, 6.31. Okay, 6.31. So there's this table, and it's got all this information, but what we would do is find that 21 degrees of freedom. And then what you do is you try to put that number where it would go inside these values right here. Okay. So that number was 6.131. And so if you look, it doesn't really fit in those numbers. It would be over here somewhere, 6.131. If you just look at those numbers, here's the smallest number, 1.3, 1.7, 2.0, 2.5, 2.8. Keep going left, your 6.131 would be over here. And so that translates to, this is a p-value, some p-value in this ballpark right here. Okay, we can see from this table that a p-value is less than 0.01. That's not very accurate. That's not very accurate, but that would probably be good enough for us to answer this question. So a p-value is less than 0.01. I'm going to write that down. We've got a p-value from table A3 of less than 0.01. Okay. Now, if you go, well, time out. I don't need to use the table because we can use StatDisk. So remember when we typed all those numbers in, those 23 data points into StatDisk, they give us all this stuff, but specifically, we can see this p-value is 0.00000. We've got pretty much zero right here. And so it's actually better that we have that 0, 0, 0. So p-value equals 0.00000, and that was from statdisk.com. Okay, so what's that tell us? Who cares? What's that mean? So earlier, we had some test that said if the p-value is less than or equal alpha, that supports the claim of linear correlation. You go back to, that was one of the first slides, the 5th slide right there is where it talked about that. So go back earlier in the notes. The p-value is less than or equal alpha, supports the claim of linear correlation. So think about what our numbers said. Our numbers were p-value 0.0000, and our alpha was this. This is the significance level. Significance level is alpha. So because 0.000 is less than 0.05, this supports the claim of linear correlation. Okay, so remember our null hypothesis assumed that there was no correlation. We just proved that that was false. Okay, we proved the alternative hypothesis. All right. So we think there is linear correlation. There's this little saying that says, if the p-value is low, the null must go. I don't know how useful that is, but if p is low, the null must go means we're going to reject the null hypothesis, reject it, okay? That means this isn't true. We don't think this is true. We think there is, in fact, a linear correlation. Now, one other thing I want to show you is with technology. Those of you with a TI, you can do a T-CDF. We've done a couple of different distribution functions, but a T-CDF, it's going to take arguments of your T value that you got from that equation, 6.131, and then it's going to go to infinity, and then you're going to have your degrees of freedom. So in this case, we can type in that 6.131, and then infinity we'll have to simulate with a bunch of 9s, and then degrees of freedom is 21. Let's see what that gets us. Oh, no, not this one. Sorry, this one. Second vars. Is that it? No. Oh my gosh, that's not the second button. Second vars and T-CDF. Lower, we're going to put at 6.131. Upper, bunch of 9s. Degrees of freedom, 21. Okay, and gets us this. Now, what's kind of weird is you have to think about if it's one-tailed or two-tailed. And I know you don't totally know what that means yet, but if it's two-tailed, you're going to have to double this. And that gets us about 0.44, let's see, 0.00004. Is that right? Oh no, 5 zeros. E-6 means move over 6 places, so let's squeeze another 0 in there. Okay, that's your p-value. And you know that supports this number right here, 0.00000. That's what we're getting right there. 0.0000044 is the p-value, but we'd still have to come up and look at this and test it with alpha, which was the significance level. All right, long story short, this is not a main idea. Okay. So here we've got the null hypothesis again, but it's to highlight the different situations, I guess. There's the null and the alternative right here. Notice we're assuming this equals 0 again. We're always assuming some parameter equals 0, but a left-tailed, remember what your normal distribution looks like. A left-tailed looks like this, and a right tail, same thing. You've got your null and you've got your alternative. But for a right tail, it looks like this. And then I guess the difference here is if you've got two-tailed, the null row equals 0, and the alternative, it's not equal 0. And so for two-tailed looks like this.